All right, our favorite topic today, orbital penetration. I'm sorry, that's what it's called. Let's just get over it. So, why do different shaped orbitals in the same energy level have different energies? And the answer is that some electrons can get closer to the nucleus than others. Now, are you guys familiar with Coulomb's law? Do you know Coulomb's law? So, Coulomb's law, it's frozen. Okay, there we go. Basically tells you that force is proportional to the electrostatic force. So I'm just going to call it F elec. Okay? Now, what does that little fish symbol mean? It means is proportional to. Okay, so the force, electrostatic, is proportional to, and this is on page 79. What makes an electrostatic force bigger? Not more mass. Mass makes gravitational force bigger. Charge, more charge. So charge works for electrostatic force like mass does for gravity. Okay? So what that means is when we write that, the bigger the charge, the bigger the force. Okay, so the electrostatic force is proportional to the amount of charge. So the bigger the charge, the bigger the force. So the more protons in the nucleus, what can you say about the force that will be exerted by the nucleus on the electrons? The more protons in the nucleus, the bigger the positive charge, and therefore the greater the electrostatic attraction. All right. It is also true that the electrostatic force, which I'm just going to call F elec this time, is proportional to, it in fact is inversely proportional to, anyone know? So the force is going to get smaller when what gets bigger? The distance between the two charges. So it's proportional to 1 over the distance between the particles. And in fact, if we really want to get technical, it's proportional to the distance between particles squared, but we are not a physics class, so we're not going to get too fussed up about it. Basically, what we need to know as chemists is that as the amount of charge goes up, the force goes up. As the amount of distance goes up, the force goes down. Okay, and that's what we need to know about it as chemists. We don't need to worry about that squared term at this point, okay? But this is the portion of Coulomb's law that we're going to be looking at today, because if we can get closer to the nucleus, the force is going to be higher, and you'll be able to lower potential energy. Okay, so the closer you can get to the nucleus, the lower your potential energy is going to be. So, penetration is the ability of an electron to get within the other shells and subshells, to get closer to the nucleus. It is the extent to which an electron can approach the nucleus. And it's going to depend upon two things. It's going to depend upon the level, the energy level, N, and it also depends upon the shape of the orbitals. We started talking about this last day, but we're going to look at some graphs with it today that'll hopefully make it a little clearer. So s orbitals, by their very nature, the electron density is very close to the nucleus. So if you're in energy level 2 and you're comparing two s's and two p's, the s electrons will be able to get closer to the nucleus than the p electrons. Okay? So s orbitals have quote unquote high penetration. Okay? In principal energy level 2 and up, there are nodes in the s orbitals. Do we remember what nodes are? No density. Nodes, no density. Oh, look, it says it right there. How convenient. So despite this, s orbitals at all energy levels have significant density very, very close to the nucleus. So if we look at the s orbitals, and these are kind of like, you know, if we did a time-lapse photograph of the electrons and just took little snapshots over time, you can see that the 1s pretty much has density right up to the nucleus, yes? And the 2s also has density right up to the nucleus. There is a node a little further out, so it's kind of like there's this little gap, and then the bulk of the density is a little further out. But we do get that one area that's like really quite close to the nucleus. Yes? Why would they be near the nucleus? For the bigger ones, they just are. Yeah, that's where they go. That's the solution for the wave equation. Yeah? I know, a lot of arm waving and shrugging. I'm sorry. Okay. So similarly, for the 3s, we have the density right by the nucleus. And then we have a node, right? And then we have density that's a little further from the nucleus. And then we have another node, and then we have the bulk of the density, which is farther from the nucleus. So that's why the 3s energy level is at higher energy. Even though it does have some density closer to the nucleus, it's not as much as, say, a 1s electron. Okay? So we're gonna take these and we're gonna turn them into a graph, okay, where we're sort of looking like, you know, like that kind of, okay, forget I did that, okay. So here we are. We have our 1s orbital, and what is, I know the words are not great quality, but this is probability here, okay? So here is the probable distance of an electron from the nucleus. Right at the nucleus, it's pretty much 0, but you go any distance whatsoever from the nucleus, and you end up with some density, and the bulk of the density is very, very close to the nucleus. This is our most probable distance of an electron from the nucleus for the 1s. If we look at the 2s, we can see that we have some probability right close to the nucleus, and then we have that node where there's like no density at all, and then we have the most probable density from the nucleus is a little further out. And 3s looks pretty much the same. It gets a little shorter each time, and the bulk of the density is sort of in that third ring. Okay. Do you need to be able to draw this graph? Probably not. Okay. So here we have a 1s orbital. So this one is because it's not colored on yours, so we can label them. This is the 1s. This is the 2s, and this is the 3s. So all of them have density very, very close to the nucleus, but the 1s obviously has more. The 2s has less, but still more than the 3s. Here's our p orbital. Let's compare these. Which one has more electron density close to the nucleus? S. It's fairly obvious, right? There's this huge node, right, in between the two lobes. So we have some diagrams here. We've got a 2p. All right, so you can see those sort of two lobes. You can see the 3p, there's two lobes, but just like the s orbital had rings, concentric spheres essentially, we have concentric lobes where again we have what's right here? That's a node. Okay, and again, are you going to have to draw this or recognize it or label a node? Probably not. All right. So there we are, there's our 1s, 2s, 3s. And here we are looking at our 1s, our 2s. So this is also 2s. And you'll notice that our 2p doesn't really have any significant density really close to the nucleus. It's very, very low. Okay, and that's why the p orbital is at a higher energy. Yeah? So that's all there is to that. So if you're ever asked to explain why, you can say because there's less density close to the nucleus, because there's a node there for the p orbitals. And then I just got excited finding, different diagrams. Here's our 3s. You can see the 3s has a nice peak close there. The 3p has a peak that's closer, and then the 3d, we don't really get much density until we're way the heck out here, yeah? It only starts to go up, and there is where most of our density is for the 3d. Okay? And I really, really wanted, and I don't know why I didn't do it, I should have put in a graph with a 3d orbital compared to a 4s, because that's always the one that's kind of confusing, right? It's like, why do electrons prefer to go into the 4s compared with the 3d? Why are those 3d orbitals at a lower energy? And we're actually going to just pull up a diagram here because it made me sad that I did not include it. Electron density, we want the 4s versus 3d. Images. Okay, where's our picture? Here's our picture. There we go. All right, so if you see like the 4s has density here. The 4p has some density here. You get nothing. You got nothing virtually with the 3D until way over here. This is essentially 0, 0, 0, 0, 0, and then it just goes up. Yes. Yeah. Because that's where the wave, that's the solution to the wave equation. It's math stuff that I don't understand. Yes? Yes. No, 4S is easier to get into than 3D because we've got 3D is here. So we have basically no density right close to the nucleus. The 4S is this one. And so the 4S gets right close to the nucleus, and so you have electrons that would rather be in there. Yeah, yeah, and there's hills that get closer to the nucleus with the 4S. Yes. There's still some really close to the nucleus, and that's why it's okay. Yeah. Okay? Yes. Yeah, the closer to the nucleus, you'll be at a lower potential energy, right? It's just like, where do things on Earth want to be? Closer to the Earth, right? So the nucleus is like the Earth for the electrons. Yeah? Okay, that's all we're going to say on that. I don't even think there's any questions related to that. I don't think it's actually going to come up very much. How much of this do you need to know? Probably not much, but you will hear the terms mentioned from time to time. So it's good to have heard them. And they certainly will mention it in university. Okay? Now, you could, if you want, do you want to do a POGL for the rest of class? A POGL? Do you guys know what a POGL is? Have we done one? We've not done one. Oh my God. Okay. Or should I just teach you electron configuration? You want to do a POGL? Okay. Okay. You may or may not like it. Yes. The bulk of it is further away, but it does get closer to the nucleus, so electrons prefer to go into there before. Okay. So a POGL, it sounds way more exciting than it is. Although, honestly, you guys will probably enjoy it. I feel like you will enjoy it. You seem like you love to talk. So it is all about talking. Okay, so this is process-oriented, guided inquiry learning, POGL. What's that? I know, right? It is, but it is like a game. It's a game for your brain. Super exciting. So on what you do in these process-oriented guided inquiry learning. You don't need to know that, okay? But on page 47 up to 54, 47 to 54, if we just turn there quickly, you will be presented with some information. But you're not going to just do it on your own. It is meant to be done in groups of 4. You can make it work with a group of 5 or a group of 3, but the best is 4. So when you get yourselves into groups, take that into consideration. It does work best with a group of 4. There are also specific roles in order to make the process work better. Okay, stop. Shut the book for a second. We have to talk about the process because it is process oriented. Okay? Okay? So, process oriented. So, you're going to have one person who is the facilitator, who makes sure you get started on time and keep on task, la 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 la, all that good stuff. Yeah? Okay? There's one person who is going to be the spokesperson. That does not mean you need to talk in front of the class. What that means is when you have a question, you are going to be the one who goes and visits another group to ask the question of another group. You can then go visit, if you don't get an answer from them, you can go visit a second group. If you don't get an answer, then who can you come visit? Me, okay? So it's meant to exercise your brain. It's meant to sort of make you learn things by discovering them a little bit, okay? Now, over the weekend, I'm going to make you watch a video that will show you like how to do it as well. So we're going to attack this again from several different directions, yes? So that was facilitator, spokesperson. There is a quality control person. The quality control makes sure that everybody's answers are all the same. They also are making sure that everybody feels good about the answer that you've come to, that you all come to agreement, that you all come to consensus about what answer makes sense. Yes? Okay. So that's where, and then the final one is the process analyst. And what processes are we supposed to be working on? Well, when you get to your group for the first time, you're going to send somebody to pick up one in each of these sheets. One tells you what each role does. And even though I've gone through them very quickly, you are going to describe, you're going to assign roles and you'll describe your role to the rest of the group. Yes? Yeah, the process person is going to be like, okay, so we need to work on personal skills. Are we good at accepting peer review, or are we being, kind of, patty to each other? Critical thinking, are we visualizing? Are we building analogies? Are we summarizing? Are we defining? Are we drawing conclusions? How are we doing at communicating? Oh, how are we doing with time management? How are we doing with information processing? Are we observing? Are we listening to others? Or are we just shouting over them? Because I know that does happen every once in a while in here. Okay, are we interpreting the drafts and model? How are we doing at problem solving? How are we doing at teamwork? Okay. When I do this with my grade 9, sometimes it can be a little more challenging because you know how grade 9s are kind of like, oh, I don't have work. I have high hopes for you guys, so don't disappoint me. All right. Now, on every role card, if you don't know what to say, if you're like, oh, I don't know how to be a process analyst, and there's some good tools or phrases used. Let's stop for a minute. I have a couple comments on what we're doing well, and a suggestion on how we do more productive. So if you need to, you could literally just read this if you have to. Okay? Or they might say, oh, let's wait a moment so this person can catch up, because you always want to be in the same place at the same time. This does not work well. I could give it to you as a worksheet, but that sort of defeats the purpose of it. So if you're just gonna like go and do it all on your own, then that kind of defeats the purpose. Yes? So you will grab one of each of these. Technically, we have like little rating sheets in the back. I'm not sure that's necessary for us to do. No, like the rating sheets are nice. It's just like, how did I do today? How was I being a process analyst? Did I do these things? Okay, but I'm not going to make you do that because, you know, if you would like to, though, we have time issues, but if you would like to, you can. Okay. They actually use this in universities. It started in chemistry in universities. Yeah. All right. So you're just going to work through it. You're going to answer all the questions together to the best of your ability, and hopefully you're going to learn something along the way. If you don't successfully learn it through this, you are going to watch a video on the weekend that will also teach it to you. And guess what? On Monday, I'm going to be going through it with you again, just in case we have any gaps that haven't been filled in by independent learning. Yes? So, would you like me to organize you into groups, or would you like to organize yourself into groups? Don't really care? You could organize yourselves? Okay, and if you don't want to organize yourselves, that's fine. I can help you out. Anywhere from 3 to 5 people is fine. Okay, so if you're a group of 2 and you're like, oh my gosh, I don't know what to do here, you can maybe find yourself another group of 2 or a group of 3. No. 3 is fine. Oh, one last thing. You want to be seated, not in a row, because that makes it hard to communicate. You want to be like 2 on one side, 2 on the other. Okay, number 5, 1 person on the end. So I see that you have your us 5. Move over. I have to get the sheets, bro. I'll be the team manager.
You gotta work on this, my boy. That's why I gave it to you. As the delegator, I think. You know what? Can we just do this, bro? Wait. How many boarders were at this boarding house at 5 p.m.? 1, 2, 3, 4, 5, 6, 7, 8. Un, deux, trois, quatre, cinq, six, seven. Why are you on this side, bro? You could have gone that side. Alright. No, at 5 o'clock. How many are there already? You're going to be good. Okay, do you guys understand what there are 8 people? Actually, that's not up to me. No. Wait. No. Okay, it's yeah. Describe how you can count. I count. Dude, you're asking me, bro. Oh, nice. Oui. Nous avons vu.